Can you hear me? Okay, good. Hi, I'm Jean-Luc, and I'll be talking about a new Python project that we've been working on that's designed to help researchers working in Python explore the data more easily and with a special focus on the IPython notebook. So what is HoloViews? Well, it's a library of declarative objects that hold your data and that can be composed together. Now, what makes HoloViews interesting is that these objects can then visualize themselves. What this means is you spend your time thinking about the contents of your project and thinking about your research and what you're trying to show, and then later you can think about your visualization aspects. Now, what does this mean? Well, I'll give you a quick demo, and and this whole notebook you're looking at here is actually available, or will be available, and contains the whole talk. Anyway, so if you're working the notebook, you can start with some simple data types, like some floats, for example. Now, if you're working something simple, just like some two numbers together, you run it and you execute it, you get something like 3.5 when you add 1 and 2.5. Now, this is a perfectly good representation. But if you start working with bigger data, you start encountering a problem. So let's just say that we have a NumPy array, and we open it up. We can see the representation here, and you can see that it's pretty impoverished. There's a lack of, the missing values, and you have kind of no idea what you're actually looking at here. So what HoloViews does is it takes your data, the contents of your data, and gives you objects in which you can wrap your data. And here's a demo. You can see that we've just passed our array into this HoloViews image object, and if you call the data attribute on this object, you get back your array. So what does this buy you? Well, if you actually look at the object's representation, you can see that we've switched to a rich representation, which is much more useful than the textual representation that you saw earlier. You can now see that's the Mandelbrot set. Now, what's important here is that the object is not talking about plotting. There's no plotting code that you can see here. This object doesn't have plotting state. It doesn't call any plotting classes or any plotting calls of any sort. So what you need to think about is when you have some data, for example, this NumPy array, what other metadata might you want to actually associate with it? Now, this is because if you don't have some metadata, sometimes your data is incomplete, and you want to keep a record of what metadata so that you understand the semantics of whatever you're trying to show. So in this particular example, you need to remember that the Mandelbrot set is actually defined in the complex plane. So in fact, the x-axis is actually the real axis, and the y-axis is actually the imaginary axis. Now, this is metadata that you can then put into your HoloViews object as follows. So you can declare this, and then you can associate it with your array, and you get a new object, which now has a similar representation. But if you look closely, you can see that the axes are now labeled appropriately based on the metadata that was associated. So the point is that even just by talking about the content of what we're thinking about, you don't need to worry about plotting code. This has visualized itself. Now, I will come back to here. So what we have is quite an extensive library of these objects, these wrapper objects, which we call elements. And if you go onto our website and you go to, we have a notebook which contains all the elements that we offer, which are self-contained. You can just run them and try them out yourself. Now, here I'm showing you another object. This is, again, just your data, and all your data is available here. So this just shows you a bunch of different elements. You can see some raster types, some sort of statistical type functions, and then you can see some 3D plots here as well, which we support. Now, because this is just your data, and it looks like a big plot, but actually it's a data structure, you can drill down into any part of this plot and find whatever was originally specified. So let's just say that we're looking at the scatter plot here. Now, you could pick any one of these points and actually and find out exactly the x and y value without any loss. It's exactly what was specified initially. So the other thing to note about this plot is if you look at these penguins here, we've got some little regions of interest. And so we've composed elements together, and this is something that was very important to us. In fact, the whole object is a composition. As you can see, we have multiple elements all put together. So this is what I'll be discussing right now. So for composition, you need to think about why we want to compose the data and what the semantics of composition is. So when you think of a publication, you often don't have just a simple scatter plot or a simple bar chart, but you want to actually express the relationships between different bits of data together. So in HoloViews, there's two ways of doing this. There's what we call layouts, which is when you want to just show some data simultaneously next to each other, and you can create layouts very easily with a plus operator. And the other very common operation is to show data on top of multiple elements on top of each other. And this is called overlaying. And this is when you show different bits of data in the same space. So back to the demo. So here's an example. So earlier I showed you this object which contained the manual set. Now we can expand on that. In particular, we can use a method on this object called sample. And what this does, if we run it, is it creates a new HoloViews object called a curve. And this is what you see in B. Now, note that the axis here has actually been labeled correctly, because the metadata that you associated with your object earlier is still available and is still used appropriately. Now, this whole object is an example of a layout, because we have one thing on the left plus the thing on the right, which is the curve. And you can see that, for example, we get sub-figure labels automatically generated for you. And on the left, what we have is another HoloViews object. This time, it contains of two things: the original fractal that we were looking at, plus a horizontal line that shows you exactly where you were sampling. So what you see here is, again, no plotting code. You don't see, there's no plotting classes. It's just declaring what your data is. And you can see that the representation is pretty useful by default. And you might be wondering, how do we start customizing all of this visualization? And we'll be coming to that in a little bit later. Okay, so, right. So another thing that's very important is, even if you can generate static figures, which might be useful for publication, you are often exploring your data when you're actually doing your day-to-day research. So you find that data sets are often very high-dimensional, and there's a lot of results contained with them. So typically, you might have a collection of results, and there's some sort of dimension over which your results are varying. Now, HoloViews actually makes it very easy to actually explore your data. For this, we offer some objects which you can use to actually dig into your data and find whatever sort of interesting patterns you might be looking for. So we have a collection of objects, some of which will let you look at your data spatially, or you can lay out all your different results over time, or finally, you can actually explore them via live interaction. So let's have a quick look at that. So in this example, I've created another one of these HoloViews image objects. And this is just a simple example created with sines and cosines and mesh grid in NumPy. What we might want to do is look at how this pattern changes as a function of, say, frequency and amplitude. So you can do this in a simple expression. You're creating an object, and you're declaring just the data, just the NumPy arrays. So what we have here is something that looks like a dictionary. It's got tuples, which are in frequency and amplitude space. So this is what these tuples are. And what we have then is these elements, which are the values in the dictionary. And you declare what you're varying over here. When you do this, my fault. Yeah, there we go. When you do this, you actually get something that you can actually start exploring. Now notice that we didn't actually explain anything about widgets. The widgets just appear based on the fact that we have these two dimensions to actually explore. So we can look over the frequency space, and we can look over amplitude, and we can, of course, look at any combination of those two. Now, these widgets actually export statically, so you can actually get, for example, put in a web page, for instance, if you want. Now, everything I talked earlier about composition still applies. So, for instance, you can actually do layouts of holomaps, and here we've got an example. So what this is doing is using the plus operator, again, to put two things side by side. Except this time, they're these holomap objects, which lets you explore them. So again, we can look over frequency, and you can see what happens. Now, the grid method creates something called a grid space. And what this has done is actually laid out amplitude spatially. And this is why you can see this axis is now amplitude. And then this is why you can see that the amplitude slider affects the part A of the figure. The last thing I'll say now is that when you have one of these HoloView objects, you can actually switch between representations very easily. We don't tie you down to any particular representation. And you can do this for elements, and you can also do it for these objects, such as holomaps. So here, what we have is a grid space. And we just simply pass our holomap into the constructor of the grid space, and we can see this. Now, the sliders have disappeared because all of our dimensions are actually right there on the page right now. So you can see frequency is now laid along the x-axis, and amplitude is along the y. So I've been talking a lot about the semantics of these objects and the fact that you don't need plotting code. But you might be wondering, how do I actually start customizing my visualization? How do I customize aesthetics? And for this, I will pass you over to Philip.
So I'll be picking up from there. So far, we've been looking entirely at how to specify the content of your actual results. So how do you get the actual data into HoloViews? And that's fine as long as you're actually exploring your data. But as you're moving away from exploration to more towards publication, you become interested in actually customizing your plots, making it look pretty, and so on. And HoloViews also makes this very easy. So, for example, we provide two IPython-specific syntax to make this very easy. It's also possible within vanilla Python, but we provide this in magics. And so we'll use this opt magic to, for example, customize the color map of this particular image. And everything here tab completes, so apart from the actual color map itself. So we'll say we want it blue, and we'll execute the cell again, and it'll immediately become blue. And there's actually two types of magic. So the magic can be executed as a cell magic, which will apply this particular option to this particular plot. Or we can use the line magic, which will apply any option to in the entire notebook. So we'll set it to reds. And now when we re-execute this particular cell, we immediately get the plot back with this new color map applied. Another thing you might want to customize about your output is the output format. And for that, we provide this output magic. Again, everything tab completes. So we can, for example, change the figure format. But in this case, since it's a widget, we might want to change it to a GIF so you can present it on your website. OK, so we'll re-execute it now as a GIF. Wait a second. Oh, that's maybe a little bit fast. So we'll now reduce the frames per second and reduce it to 2. And now we can actually see what's going on. We can see that it varies one dimension after the other because, of course, you can only display GIFs linearly. OK, so that's two types of customization you can do. But different backends are actually suited to different tasks. So matplotlib is very good for publication quality plots. But backends like Bokeh, for example, in which we have now implemented a prototype backend, Bokeh allows you to actually interactively explore your plots. So the idea is that you can dynamically switch the backends and immediately, depending on the task you're performing, and here you can immediately zoom in and out and actually use all the interactivity that Bokeh provides. OK, so now we've seen high-dimensional exploration and how to customize and composite different plots. And that actually gives you a lot of power. It gives you a lot of power to create complex figures using just the simple element types that we provide. However, to generate more complex plots, and in many fields you require very, very specific customization, specialized plots. And for that, we allowed HoloViews to be easily extended with new element and plot types. So I'll show some examples of some plot types. So here, this particular example is just a visualization of some EEG data from a machine learning challenge I participated in. And it uses just the standard HoloViews element types. Here, we've used some simple points, overlaid some text annotations, and we've got a side histogram, and again, it animates just like any other plot. So we can actually see what happens over time. OK, so that's just using the standard elements again. However, one of our users actually works in quantum physics, and he needs some specialized plot types. So here in A and B, again, it's just standard HoloViews element types. It's some images with some contours. And here we've actually marked a subregion of interest, which is then expanded on in figure B. But then we also have this new plot type, which is called a Bloch sphere. And because it integrates with HoloViews, because it integrates outputs to matplotlib, you can integrate it with HoloViews very easily. So it now supports all the different functionality of HoloViews. You can easily integrate it, lay it out, just like any other HoloViews plot. You can animate it, just like any other HoloViews plot. And you can actually, maybe more interestingly, we can see what happens if we explore this. OK, so that's just one element type. There's very many, so I've actually been working on an extension for geographic data using matplotlib basemap. And so you can see that here. And that's just one example. But to take advantage of HoloViews, you really need to integrate it within your own code. And the way to do that is just to export HoloViews objects directly. The easiest way to do that, anyway, is to export HoloViews objects directly. So all you do there is wrap your data along with your metadata in our HoloViews objects, export it to the user, and that actually requires none of the dependencies, so you don't actually need a plotting backend to export any of this, but then the user can explore this data and immediately gets the visualization, which can actually double as a GUI. So for example, for our work, we work with a neural simulator called Topographica, which again outputs HoloViews objects. And in this particular example here, this is a simulation, some results from a neural simulation. And you can see, again, all the data here is available. You can animate it over time. You simply compose it together and explore your data. And it's all still there, so it's not a dead end. You can always get your data back out. You can export it to pandas simply by calling a particular method, or actually access the data itself. Okay, so that's one aspect. I'm not going to switch back to this. Another important factor is reproducibility. HoloViews actually allows you to span the entire workflow from initial exploration to publication. You require less code to actually explore your data. Everything is self-contained, so as you see, all our plots were very little code. The raw data is always accessible, and HoloViews provides facilities for data comparisons and notebook testing. So all the notebooks on our website are actually tested daily to ensure nothing changes. We allow exporting and archival of plots and notebooks. SVG, we can export to SVG, which means that you can go from, you can initially explore and then export everything to SVG and actually embed it into your final publication. Okay, so finally, to conclude, HoloViews helps fulfill the promise of the notebook format. It means readable documents interleaving visualization and text with minimal clutter of plotting code and additional plotting code. All your data is always at your fingertips. You can always associate metadata and semantic information with your data. Complex visualizations become very, very easy, and that's how HoloViews allows you to span the entire research workflow. Okay? Thanks, everyone, for listening. This actually doesn't fit, but all our features don't fit on the page, apparently. So tutorials and examples you can check out at holoviews.org. You can pip install HoloViews and conda install HoloViews. And that's it. Thanks, everyone, for listening, to our users and our supervisor, Dr. Jim Benning. Any questions?
I take it that means you'll want coffee then. Oh, no, there's one here.
Oh, sorry.
My bad.
You said that your widgets were, you could export them as being static. Will they go into NBViewer?
They will work in NBViewer. Currently, we're still, sorry?
Repeat the question.
Oh, sorry. The question was whether the widgets will actually work in NBViewer. The answer is yes, they will. Just out of the box, basically. GitHub integration doesn't quite work yet, but we've asked them. Any other?
Questions? If not, let's thank Philip and Jean-Luc again.
Great. Thanks very much.